Welcome everybody to this new session of the seminar Philosophy of Science. Today so it's a pleasure for us to have as a speaker Jean-Baptiste Joinet, who is, besides being my former supervisor in Paris 7, Jean-Baptiste was associate professor at the philosophy department of Université Panthéon-Sorbonne, Paris 1. From 1993 to 2012. Since 2012, he is full professor at the philosophy department of Université Jean Moulin, Lyon 3. His specialties cover, on the one hand, interactions between mathematical logic, in particular proof theory, and computing theory, proofs as programs and proposition as types, correspondence, implicit complexity, linear logic, typing systems. On the other hand, history and philosophy of logic, particular constructivism, foundations of logic, abstraction and classification, negation, theory of definitions, and finally, computation theory. In particular, he is a specialist of algorithms, computability, complexity, types, physical determinations of computation. Today, Jean-Baptiste is going to talk about indiscernibility and classification, from Hermann Weyl's creative definitions to the notion of type. So please, Jean-Baptiste, thank you for accepting the invitation. The floor is yours.
Okay, thank you. So unfortunately, I will not speak in Portuguese today, even if I am able to. I'm the unique member of the Association for the Promotion of Portuguese as an international language. But apparently there are some people who don't speak probably online. So I will speak in English. Today, okay. So we start by, because I'm not aware about the public, and there are some mathematicians, some philosophers, maybe some historians, so it's a little bit complicated to find the good scale. But I will start with a historical background about the Peano School approach of ideal elements with the theory of abstraction in the end of the 19th century. So in the end of the 19th century, the new logic, which is not burning, but which is happening to board, say in English. The Peano School launched a program for classification of to understand what is a proof, a demonstration, but also they try to do a typology of definition, mathematical definition. So, briefly speaking, there's a lot of hesitation on the more details, historically speaking, but they make a distinction between implicit definitions, explicit definitions, and definition by abstraction, on which I will focus on today, even if I will just recall quickly what are the first one and so on. So implicit definition, loosely speaking, are what we could call axiomatic definition, or implicit definition is a name coming from, I think, jargon in the end of 19th century, but also Poincaré speaking about déguisé from French definition déguisé, which means I don't know what to say in English, but which means definitions with the name, without the name definition, so to speak.
What was it in French?
Déguisé. So it's definitions, but without the name definition, so to speak. So definitions.
Disguise.
Disguise, yeah. Okay, disguise.
In disguise.
Oh, okay. Disguise definitions. Something like that. But I think in English there is another meaning, so that's maybe means. So an axiomatic, even if as an axiomatic, that doesn't have a specific form, but it has some desirable properties like to be consistent, etc., etc. So, well, I will not refer on this today anyway. The second kind of definitions are what I call here explicit definition, which, so to speak, is what is traditionally called nominal definition, even if nominal as opposite to real definition, this medieval or from Greek time, the distinction is not very relevant, or Latin time is not really relevant. But anyway, I will not focus on that. Just to recall, because it's too long, so just an example here, I mean, a generic example is very simple. For example, if we in a definition where there is a new word introduced, a new element of vocabulary, for example, here binary predicate binary relation R, and the definition is a new axiom, is a new statement that we put in our current theory, but in a very specific form. In the case of a binary relation, for example, we present the binary relation in an atomic way. So it just says it's binary because here we have two variables which are different, and it's not part of a bigger formula. So it's an atomic presentation of the predicate R, the binary relation R. And here we have a maybe big formula, standard formula in the current language, and the only things that, or almost only things that we ask to that part of the formula, which of the definition is called the definiance, is that R don't occurs in the definiance. And also some formal things like typically the best would be that we have exactly free variables in the formula, something like that. But essentially, when we have, so it's a new axiom with a specific form, and the specific form has mainly two consequences. The first consequence is that it is eliminable in any context, because here it's presented as an atomic formula. So in any place where R will occur, you can replace this by that, because here it's a double implication. So it's possible to chirurgically, chirurgically is French, I think, surgically, you can put R away and put the definiance in the same place. You can substitute in any context, because it's atomic. And the second consequence of that, the consequence of this eliminability of the definitum, is that it's conservative, which means that we cannot have any statement that we can prove before the introduction of the definition, so which is expressed in the language without R, can be there is no new theorems in the formal language. Okay, there are new theorems in new languages because before the definition was not present, but now it's present, so we can say some things about R. But everything that were proved on the formal language still was provable without the definition. So what the notion is known as conservativity. It's conservative. The introduction of the definition axiom is conservative over the language of the formal theory. Okay, so this is the only thing that we have to recall: a specific form, which is that one, in the simple case, but eliminable conservative. So the third kind of definition called by Peano School definition by abstraction, the Peano School or Chieri, it's a group of say something like 6 famous mathematicians at the time in Italy, close to France, or the city, Torino. So they apparently it's like a really historical experience. Or they took a lot of examples in the history of mathematics, starting from the antiquity, and saying that there are some way to introduce new words which are not axiomatic in the usual sense, not the nominal definition, but which are of the following form. So maybe start with 3 examples, the very famous, usual examples that we give when we explain what it is. Maybe it's better to start with the second one. So here you have to imagine we have only lines, okay, lines and points, maybe lines, and we say that 2 lines are parallel when there are all the points in common or no points in common. And then we will introduce a new element of vocabulary, which is D, or D of X, or the direction of the line. So a priori, the direction of the line is not a line, it's not a point, it's a directional right, a new concept. Could be things like that. Anyway, it's a new word, but we don't say what is the direction of X. Don't say direction of X is this thing or another one, but the axiom introduces directly the direction inside an equality. Okay, so we say the definition is not what is the direction of the line, but in which condition the direction of two lines are equal. So the definition by abstraction has this particular form. It's a new axiom, a definition, maybe definitional. We'll see, we'll discuss that, which has this form. A second example, famous, is the notion of cardinal, where if there exists a one-to-one correspondence between two sets, we can say that they are the same cardinal. Okay, so we don't say what is, we don't say what is the number of element, but we say when we can test the equivalence when there is and the third one, which is also the same form, but for the fact that we are not, it's not applied to one X, but to a couple, another pair of X, but it's the same idea. It's coming from the antiquity when it comes to define what is a rational. So we are in a Pythagorean world. There is only integers, and no place for number with comma and decimals and so on. So what is the status of a rational number? Here we don't say what is the rational number, but we say when we can say that two pairs of integers define the same rational numbers. So we say that more or less when x on x2 and x3 on 3 are equal, so which is well these projects. Okay, so here are three examples, which and there are milliards of such examples in the history of mathematics, in particular in the 19th century, where this grew up and becomes very frequent. And the Peano School sees all of these examples and try to understand them as a unique scheme of definition. And they will produce that proposition that means that they all have this shape. If we introduce a new symbol, a function symbol, a unary or maybe binary, we can see it as a unary symbol. So of that form, where here we have a predicate, where F don't appear, where in all of that case, the predicate, the formula here express what they will call an equivalence relation. So they will identify that all the examples that we saw, and all the examples of the other one, the formula which is here, which is a definitum, has the property to be what they call reflexive, symmetrical, transitive. Actually, there are some other terminology, but it's the terminology that is nowadays standard. So, and they don't speak of equivalence, equiform, in Italiano si dice ugualiforme, una cosa così. A word of this sort. No, ugualiforme. As an identity. Okay. So they call this kind of definitional axiom and definition by abstraction, and there are so what we call today of this form, where here we have a property which express and what we call nowadays an equivalence relation, and where F is a fresh element of lexicon. So actually, it's not only that experimentally we can check that all the examples of the history, it's an equivalence relation. It has to be an equivalence relation, because here we have an equality. So if it was not, for example, reflexive, this would be that the equality will not reflexive itself or transitive. So not only it is by definition, we say it's a definition by when it is a equivalence relation, but to add such such an axiom, in case A is not an equivalence relation, will be inconsistent. So we will lose dramatically the property of to be conservative. To add such an axiom, in case A is not an equivalence relation, just renders the current theory inconsistent. Okay. Yes,
just to be sure.
Yes.
So conservativity is kept from the definitions, from the explicit definition. Is a property who is in the case.
Conservativity means that if you add the axiom,
Yeah.
you want that any theorem provable in the formal language still you don't get new theorems in the formal language, which means that the meaning of the vocabulary doesn't change.
Exactly. So, but you presented this for the case of implicit definitions, but you're saying that this.
No, for the moment, I didn't say anything about conservative in that case. It happens that in first order theory, they are conservative. To add those axioms is conservative, but not in general, not in particular out of first order languages. So it could be in particular in the Frege definition of cardinals and so on. It was the beginning of a long story because it's just inconsistent in general. Okay, so some remarks about the terminology of Peano School definition by abstraction. So first of all, maybe why definition? So it's an as in an explicit definition, we have a new element of vocabulary. So it looks like the idea to give a name to some new thing. So what is usually in explicitly stipulatory definitions, nominal definitions. However, contrary to the case of explicit definition, first of all, the axiom, definition axiom doesn't present the essence or the meaning of the term. So we don't say f de x is that or that. We just put it in a given context on the other. So it's not completely clear what it means. As Simon Kozu actually just a repetition of I don't know, remember the sentence of Peano or one of the members of Terror, but it's exactly it doesn't say what is the entity, but more speak about the condition of equality of the entities. And it does not allow, they do not allow the inability in any context, because we can only eliminate f in an equality. If there is not an equality, we have not fx equal such or such, so we cannot replace f of x by the difference. We only can get rid of f in the specific context. This is very just, so it's not eliminable in any context. But it happens that it's conservative in the case of first order theories. So I will not insist on that. Actually, there is no slide on that, but it's the case. So there was a lot of hesitation. It's very interesting. This I recommend the reading of Mankozu, Abstraction and Ideality, the first part of the book. The first part is only on the history of that, and very interesting. And there is also a text of Consuegra. The name of the text is more about Russell, but there is a big part of the book is about the history of definition by abstraction in the Peano School. Historically, it's really interesting. It's interesting. So there are a lot of philosophical question of Peano School about are this kind of definition creative, because they are not in many contexts. The new where live the new entity of which we are speaking. So there is the word abstracta. It's not, for example, it's not a line, it's not a point, something new, direction of a line, or if you think to a number with the decimals, so it's not an integer. So where is it? So now abstracta. Are they real, or well, there's a lot of philosophical discussion about that. Now, why by abstraction? So the idea, the general idea is that abstraction in that case has been understood as subtraction. Subtraction of what? So to abstract means to neglect, forget, subtract something. So to to subtract differences. So here is a line, here is a line, there are different lines. But if I think then from the point of view of the direction, I consider as equal from the point of view of direction. So I forget everything which makes them different. That's the idea of abstraction, the use of the model abstraction in that case. And the idea will be the idea to that now the new the definitum speak about those notions which are abstracta by expressing an equivalence as an equality. Okay, I will just recall some of the three main epistemological questions that the Peano School put in the debate at that time. It's a lot of 10 years speaking about that. So there are mainly three philosophical or epistemological questions. The first one, in which sense there are definitions, because they are not eliminable, which we are expecting that the definition, if to define something is just to give a name to something, we want to be able to get rid of the thing in any context. It's not the case. So in which sense there are definitions. In general, for given Fs, when we add the set axiom, there are multiple interpretations. For example, although parallel lines have the same direction, but they are also parallel to orthogonal to the same line. So in some sense, maybe that is the direction which is defined by those lines, and so on and so on. So they are not a unique interpretation. If you think more model theoretically, it's clear that generally there are many models. And but at that time it was not so clear. And finally, are the if we think ontologically speaking, where are living those abstracta, are special entities or which kind? If we consider that lines are concrete, for example, is the direction of line something concrete or only completely abstract? That kind of question. So between the 80s, the end of the 19th century and the beginning of the members of Peano School and Russell and Frege, I forget here, progressively construct canonical set theoretical interpretation for definition by abstraction, which is nowadays very well known under the name of quotientation by an equivalence relation. I will recall this in a few slides because Mattia said to me that I cannot be sure that everybody in the public knows that. So I will use 2 slides to recall that in a few minutes. So all of this was completely clear, even in reality by Peano, by Pierry, I said Pierry, a member of the Peano class, that any equivalence relation will induce a partition of the set on which it is defined, as we will see in a. So, but what is important here to understand, because it's part of my talk, will be to give another interpretation than that one. When we have a definition by abstraction, if we think set theoretically, if we have, if we accept the notion of set, etc., then there is a given unique standard solution to interpret the famous new definitum, the function which is introduced by a definition by abstraction. So, if I will treat separately the 3 epistemological questions. So the first one is the first one was in which sense there are definitions. For Russell, it's clear there are not definitions. Change the name. It's not a definition by abstraction. Abstraction principles. It's an axiom because possibly in general case it's not clear that it's conservative. Anyway, the definitions are not eliminable in any context. So they are not really definition. But okay, that's the first answer that Russell will give. The second one was a question about how to choose among the multiple solutions that we have. So Russell make this remark that all mathematical properties of the supposed common property are completely served when it is replaced by the class of terms having the given relation to a given term, so what we call equivalent class, that we call now what it means. So in two words, this means that in any situation, there is a canonical solution, which is given by set theoretical means, which is the idea of a quotient. So if you accept set theory, or is the notion of equivalence class, so minimum, a little bit of set theory, there is a canonical solution to interpret what is abstracta, what is designated by f of x when we have. So in 3 slides, for the young students, which are maybe online. So if I have a set x, and I will equip the set with an equivalence relation. So here it is equivalence. That's a relation which is reflexive, and anyone is in relation with itself. It's symmetric and transitive, which means that if I have someone on the second, if I have two rows which are composed, there is one shortcut. Okay, so that's an example for an equivalence relation of a set. So it's typical relation which is called an equivalence relation. So I will just put color to distinguish 3 subsets of the set which are naturally induced by the relation separately, because they are made of subsets where everybody is in relation with everybody, and only 2 such subsets there's no one in relation with the other one. So this induce what is called a partition of the set. A partition is something like a classification, if you want. You distribute, for example, I will distribute all the strokes with English to subgroups, and so completely separately, any stroke is classified, and no one is classified twice, and so on, so on. So it is like a partition of the set. That's called the partition of set. And which means a repartition of all the elements of X into non-empty disjoint classes. And in that case, we say that, for example, we call this subset is called the one class, another class, and we also add the notion of class of an element. For example, the class of 2 is an element. The class of 2, which is not as so, is the set of elements of X with which 2 is in relation. So actually, the class of 2 is in relation with itself with 1 and with 2. So it designs the set 1, 2, 3. Okay, so we can define not only see with the R's, but define from the not only abstractly, as for example, I could define a class as being a subset which is saturated by the relation and maximal for this property, which is a way to define that, but complicated, and if you think here in the infinite case, but here we just, if I want to define that class, it's enough to grasp one element like 2 and looks everyone with which is, and so I'm defining the class, but from the Earth, so to speak. Okay, so what is standard is that the set of class, one class, two class, 3 class, the set of classes is called the quotient, and that's the idea that we are dividing the set in subclasses. Okay, to sum up, this was an example, but it's just a consequence of the fact that the relation is reflexive, symmetrical, transitive. So any equivalence relation induces a classification in the sense of classification, which is called a partition, this kind of classification. So that's the theorem of Peano, made clear by Russell, and made completely clear by Birkhoff. Don't remember when. Okay, but which is a standard construction of nowadays, completely standard. Okay, I come back to Russell's answer to Peano's questions. And so we understand the sentence of Russell, because we have this construction is completely canonical, any equivalence relation induce a partition. So we can just think that F can be interpreted as the class of the F of X can be always interpreted uniquely as the class induced by X. Okay, the class of X. So the solution about the multiplicity of interpretations, there is necessarily a canonical unique interpretation to interpret F as class of. Okay, that was it. And thirdly, and finally, about abstraction, as soon as you consider that sets are not abstract, which is not evident at all, but there is this canonical interpretation, so we don't need abstractors or like Platonician objects which will live in worlds that it's not, or the only one that we need are sets. Okay, we don't just need sets as a referent for the abstractor. That's the idea of Russell, and that's why he exactly say completely servant, but it's represented by the class of terms that is a given relation to a given term, so the equivalence class. It is enough to interpret what our abstractor are doing. Okay. As we saw, Peano Russell's approach connects abstraction, defined by abstraction, to classification. In a sense, Russell on Peano School says that the canonical way to interpret abstraction is this kind of classification, which is produced by equivalence relations. So, in a way, this work transforms the abstraction question into a classification one, and with this idea that to classify means to share out elements in such a way that those which are jointly classified are indiscernible from some point of view, which is given by the equivalence relation. Okay. But I will focus now on that sentence which I pronounce, which is actually frequently formulated in that context, but that I find obscure. And a big part of this work is just to try to clarify that. What do we mean when we say that equivalence relation express a relative indiscernibility? What it means? Yes, it's equivalent, but if you say one existence or one preference, where do you hear the indiscernibility? It's not so clear actually. It seems present but not so clear. Okay, I wanted the clarity on that. So the part two of my talk will be precisely devoted to clarify this idea. And so, okay, let's go. Okay, I will start the second part by focusing on the idea of indiscernibility. So there is a long tradition of about indiscernibility, and that's the most famous people in that area is Leibniz, with the famous principle of indiscernibility of the two principles about indiscernibility. So usually the way to translate in predicate language the logical predicate language, the idea of Leibniz is that is to use this formula of second order predicate logic, which says that X and X prime are indefinable if they are exactly the same properties. And if you have exactly the same properties, if you have the universal quantifier of the properties, which is second order, it's just this formula saying that that's exactly wrong. Some specialists of Leibniz that I know very well say that actually it's not exactly what Leibniz, and it's more complicated, but it's the way traditionally if you go to Stanford encyclopedia or a lot of literature, just translate the idea of indiscernibility in that language that way. Okay, so the kind of indiscernibility which is caught by this formula, there are two adjectives to qualify it. First of all, it's absolute, which means that it's universal, where X and X are completely indiscernible. That's the idea, absolutely, okay. And the second is what I call monadic, because we are using monadic predicates, so we are speaking of property that's very Aristotelian in a way. It's like things which are alone, so it's in the world, so to speak, with their essence. Is essential if you want. Okay, but we are not really interested on that, so we are not concerned here about absolute indiscernibility, so I will drop the quantifier. And so to speak, and as we see, we will extend to non-monadic indiscernibility. But about what happens in terms of classification if we just drop the universal quantifier, so if we just keep that, whereas the situation which I qualify here the Porphyrian classification, which maybe you know is the Porphyrian is epigon of Aristotle, with the idea that we classified just by predicates, so you are a man or you are not a man, and then among those which are not a man, there are those who are mammals or we are not mammals. So it's a classification which is may make a partition of the world for at each step, but a p-partition. So either you have the property p, and then you are classified with all those who have the property p, or you are not the property, and then you are on the second one. So it's like two classes complementary, or in some case maybe only one classes, but when there are two, there are two. So this way of classifying is a partition, but a b-partition. Okay, so it's Porphyr which organize a big theory of that. The idea comes from Aristotle, but it's more Porphyr. So in the medieval time, in the early medieval. Okay, and the monadic Aristotelian point of view here is to lower as we will see. So we will now we will consider indiscernibility, but from the modern, in the sense of the end of the 19th century, the relational point of view. So if we consider the relational, not absolute, so particular indiscernibility with respect to some, to simplify binary predicates, I mean, there is no problem to generalize to more than binary, but it doesn't help, it doesn't add nothing deeply. So it's important to understand that we have two notions of indiscernibility, which is produced by so it's well. For example, I will start directly with this, which is more clear. So here I have two relations, relation R1 or R2. So let us have a look to R1 with the situation some elements are in relations or not. And we can say that 3 and 4 are indiscernible from the point of view of the relation because there are targets. I use the target and targeted is graphical, okay, like rows and target, because there is no, there are discernible as targeter, as for example 3 targets fine, but 4 not, so you can distinguish them. But from the point of view of 2B target, we cannot distinguish because all the targets, all the elements with target 3, target also 4, so you cannot distinguish them from that point of view. Here, okay, but we can distinguish them from front of them, okay. And here we have the dual situation where 3 and 4 are not distinguishable because they are target exactly the same elements. So I cannot say, oh, but 4 target 2 and 3 not, because they are target exactly the same. But there exists an element with target 3, but not 4. So yet there are two notions here that I called so there are as target or as targeters, so to speak. And I will introduce a terminology, useful terminology. So follow me. So here's the terminology. X and X prime are equitargeters if their targets exactly the same, or equitargeted if they are targeted by exactly the same. Okay. So now here here is the notation targeter, targeted. Okay, they are equitargeter or equitargeted. And now is the definition, so which says that X and X3, for example, are equitargeter if they target exactly the same elements. Okay, and here if they are exactly targeted by the same elements. Okay, so but well, that's the precise definition. I'm actually probably well, I think to have a notion because the name will give a good intuition of what happens in the graphical setting. So a small proposition which will give a lot of meaning to the talk is that we can reformulate the definition of what is an equivalence relations, reflexive, transitive, and symmetrical relation. Is that an equivalence relation is exactly a relation which is equal to its So I call those two notions I don't know, maybe there. They are equal to the indiscernibility predicate, so the two, they induce. Any relational R, if you have a relational R, it will induce two indiscernibility relation, equitargeted and equitargeted, which is parameterized by R. It depends on R, of course. And on some relation, like equivalence relation, are equal to their indiscernibility relation, equal to that one, and also equal to that. And this characterizes the equivalence relation. So to be an equivalence relation means to be equal to the indiscernibility predicate in case that are induced. Okay, show them. Okay, so it's another way to define what is an equivalence relation. But say that way, it gives insights about all what is said about indiscernibility, because now it's not reflexive, transitive, Euclidean, or I don't know what, but they are equal to the indiscernibility predicates that are induced. So which means we can really think to definition by abstraction in terms of indiscernibility. Now it's clear. Okay, it's more clear it's clearer than before. Okay, but it has some consequences. Also, not only in terms of clarity, it means that as when we have R, which is an equivalence relation with those equalities, it means that in the definition of, in the formulation of definition by abstraction, we can replace the condition here R by the inducibility, any of the two induces. So we can reformulate Peano, Weyl, Russell definition by abstraction that way. Says that it's a definition, it's an axiom where we introduce a new symbol F, and now where there is an equivalence relation, we will say that f of x equal f of y if and only if they are indiscernible. When I put the two means one or the other one, depending on the context of what we belong to. Okay? So it's just a reformulation by the synonym. When there is an equivalence, there are synonyms, so I just put one or the other ones, just replace one name by another one. Okay, so the advantage, give an explicit reading of standard abstraction definition in terms of indiscernibility, now, really, relational one. It makes science which part of indiscernibility is caught by Peano Russell abstraction, namely when R is an equivalence and X is in relation with X prime, then they are indiscernible. But it underlines that it's only a very narrow part actually of indiscernibility which is used in the case of definition by abstraction, because the condition R is an equivalence is not needed at all actually, because as we will see, more or less again, the relation of indiscernibility is itself an equivalence relation. So we don't need to ask R to be a relation to say the consistency. If you remember, I said if R is not equivalence, the axiom is consistent. In that case, if I formulate it here, I drop that. This is already an equivalence relation, so it's still consistent. Okay. And no the conditions that it's the fact that we don't need that in relation. So R being an equivalence relation, being a universal requirement, we drop it now. So in three steps, one just gets the following generalization of definition by abstraction. So the first step was actually there's two steps, two steps. The first step is to 1 to 2, and the second to 2 to 3. So 1 to 2, we just replace R by indiscernibility, which is what we just saw. Okay, because in case R is an equivalence, those two relations are just equal. So those relations are equal, the same. And then I will just now generalize by dropping the fact that it's an equivalence, because here is already an equivalence one, so I don't need that to impose here that R is an equivalence. So more generally, I'm saying that I can introduce F for any situation where from the predicates that are relative to the relation R, any relation, they are indiscernible. Okay, so I did that a few years ago, 4 years ago, something like that. And 3 years ago, I discovered by chance reading Hermann Weyl at the very beginning of its biography. In the text of the beginning was that he already said exactly the same thing, namely that we have to. He don't speak really about indiscernibility or so on, but clearly the definition is the same. So speaking about relational indiscernibility, and he introduced exactly saying that he calls this kind of definition axiom creative definition, and he says that there are more general than definition by abstraction. Also, I will go that way a little bit, but there is the approach. So, as in the case of Peano, it seems to be very empirical, not theoretical about what is indiscernibility, abstraction or not, but he gives a lot of examples from the history of mathematics of definition of creative definition. So, actually, the list of examples that he gave, there's only one which is not definition by abstraction, which is definition of circle. So it's a little bit complicated to see completely the place in the history of definition creative, which are not definition by abstraction, as we will see. But also, we don't even try to give a set theoretical counterpart to definition, creative definition, as I said. So he knows so the equivalence class solution for equivalence solution, but he doesn't even try to give a hint about a set theoretical solution more general than that one. And okay, so as indiscernibility is itself, each kind of indiscernibility are themselves equivalence relations. In which sense do we have here a generalization? As Weyl says, it's more general, but in a sense we can say it's more particular. It's just a particular case of equivalence relation. So in which sense is it particular? It is not very, doesn't develop really the point. Well, there is the fact that conceptually they are more clear. It's not really to be more general, but it's more clear. It speaks about indiscernibility directly. But I think here is the answer is that more than to try to understand why creative definition are more general, it's better to try to understand why definition by abstraction are more particular. In which sense they are particular? That's a remark that he makes. He says that through hilbertian in mind, he says that we can get of infinity. And what this means is that in the particular case of the relation R is an equivalence relation, it happens that we can equalize indiscernibility and R. We saw that. So which means that when we want to test indiscernibility, which for all statements, you have to test where everybody is indiscernible, then we can just have to test. Well, for example, I want to know if two sets are indiscernible from the point of view of cardinals. So which means that I have to check that for every set, if I can have a bijection on one corresponds to one, it's possible. So, but it's infinite. Okay, so to test the indiscernibility, I have to make an infinite test. But in the case of equivalence solution, I have only to test between them. So the four disappear. So here we will see what is more particular in the particular case of definition by abstraction. And there are also some other things that we'll see later. Okay, so in my third and last part, because finally I deleted the fourth one, which was so huge, maybe not adequate. I will go now from this ideas about legacy, but indiscernibility to the notion of type, given notion of type that can be present. There will be only one slide mathematical, again, deeply. Okay. So we saw that in the case of the Peano School of definition by abstraction, there is this idea to replace the problem of abstraction by the problem of classification. So that is the canonical interpretation of the definitum as a class operator. So we interpret the abstract as the equivalent classes. So in the case of definition of abstraction, the process that's the partitioning process which is involved, which is induced by equivalence. So such classifications of kind of classification are very specific form. In particular, every element is classified only once. That's a partition. But this way to classify is actually very narrow in a sense. When we classify in the real life, one faces other alternatives than partitions. So the first alternative that in general that are classifications which are not partitioning. If you go in a library, a book is classified in, not only once. Is to be classified from the point of view of authors, from the point of view of thematic, from the point of view of, so it's multiply classified. It's not a total partition. And the second alternative that we will face is the fact that in the case of equivalence relation, the criteria for the classification is internal to the set, so because the relation is over the set. But we will see that it's possible sometimes to have, I want to classify people, I don't know, but from criteria which are not only the elements that I'm classifying, criteria coming from another set. So, which is with more general classification. So there are two alternatives here: to renounce to partition and to include also criteria which are external to the classification, the classifier set. So just because I'm not in the mathematical department, but in the philosophy department, no, in the philosophy laboratory here, just a little bit some comments about the two alternatives, both alternatives. So. Well, there is this argument about real classification or not partitioning, so that's practical reason. But if you want to be a little bit more abstract or conceptual, what philosophical arguments can we have in favor or disfavor of partitioning classification? So first of all, I think we can speak about the ontological parsimony, which means that when we have a set, and it's not so easy, but it's true that a partition cannot have a cardinal greater than the set itself. In the finite case, it's evident because it's a division, but in infinite case, it's not so evident. And actually, 4 years ago, it was equivalent. The conjecture was that to say that is equivalent to the axiom of choice. So it's not proof that it's equivalent to axiom of choice, but with the axiom of choice, you can prove that the cardinal of the partition is not greater than the set which is classified. Okay, so which means that even if we interpret through the idea of partition, we have no more elements. In a sense, it's an answer about this question of the Peano School, where are living the abstracta. Maybe in set theory, so it's maybe a richer more, but not more. Finally, we can continue to code them with integer, for example, if our enumerable, so something like that. So ontological parsimony, that's the first thing. And the second one is probably from a more practical, but the sort of mathematical practice point of view. So it is what I call the epistemological efficiency. It's clear that we are not, in general, we are not repairing. It's not English, but we are not looking at the equivalence relation just by because there are, but we use them because generally they are congruent. So there are some structures, some operations which are compatible with the equivalence relations. That's the reason why we are using them, because we can not only go to the quotient but continue to say some things at the level of the quotient. So in the mathematical practice, this idea of congruence, of compatibility is very important, and probably I'm not sure. This way, for the moment, I wasn't that way, but we have to generalize the idea of compatibility when we go outside of the side of the frame of equivalence relation. But from the purely classificatory viewpoint, partitioning is too narrow, as I said. In real classification, real classes do intersect. So they are simple, but in a sense they are too simple, too narrow. And historically, there was early attention to non-partitioning classification, notably just after all this work, Russell, Norbert Wiener, who was a PhD student, which was not position in the same place as Russell. They fight, I think. Apparently, Norbert Wiener was very arrogant. And Rudolf Carnap also. So there's a lot of literature from the beginning of the 19th century, the intersection of logic and sensory logic and philosophy, epistemology, and phenomenology also. We're trying to use this idea of classification or variation of the idea of classification to make sense. Okay, I will not go that way, but also, and I will go that way even if we will not see that. This is notion of types. So the notion of types, there is a history of notion of type coming from Russell to save logic after the failure of set theory. But there is also the tradition of type in computing theory. And in that way, types there is one way to see types in computing theory, where it's a tool to classify programs, classify dynamics of programs of computer science. So in that case, there is a methodology called here the bi-orthogonal closure, and I will present it in a few slides. Okay, so it's where the notion of types will come. Okay, yes, I think it's good. So I will start by recalling. So I was the preceding slide was about the alternative one, which means to get rid of partition, maybe to have go to classification which are more complex. And the second thing is alternative two, so to have a criterion for classification that could be external to the set which is classified. So I just here recall what we saw before, so the generalized abstraction definition by abstraction, just to replace it. But in the case of the relation is compare any relation. So now to say that we can be more general, this means that here we can replace R, any relation over X, by R is any relation over X. Not from X to I. So here it should be one more slide. So I will just I take it insert X on Y on a relation, not necessarily an application, which something like that. Okay, any relation. I still continue. You can continue to have a notion of indiscernibility. For example, those we had those ones. They are indiscernible from the point of view of the relation because they are exactly targeted by the same. Okay, so the idea of to be targeted or to be targeted, I define it on a set, a relation equipped one set, but we can generalize easily to a relation from a set to another set. I said that two elements here are indiscernible, they are mapped exactly, they are targeted exactly by the same number, and here two are indiscernible if they targets exactly the same. Okay, so the idea can be generalized easily. Okay. Unfortunately, there is one slight missing. It's not the idea is the same, targeter, and the fact that the relation is over the set X or from X to Y doesn't change anything. Or
because you put there X, R, X prime, and then TR and TD.
Okay, that's wrong. That's wrong. That's wrong. Which means that here, when we have two sets, we have to distinguish indiscernibility that way, and we say the usual word is left or right, with left, right, okay? And we distinguish from a given relation. So here you have to put only one, which is probably targeter. Okay, I have to do it. So yes, okay. Okay, that's the last way to generalize. So I think maybe the next slide make all the generalization. So the old Peano definition by abstraction was f of x equal f of x prime if x are x prime for a given relation. And now the more general form is here we have indiscernibility, only one there, and from a relation from x to y. So the more, so we have we generalize in two ways. Is the criterion will be external and classifying this from criterions coming from another set, and we will see now that we are out of partitions too. Okay. So now I will present the bridge from indiscernibility in that sense to the notion of types that I was speaking about before. So I will present the notion of type after, but just I announce the bridge itself. The bridge says exactly indiscernible elements are exactly those who belong to exactly the same types, as we will see, which even if I will define the notion of type in 1 minute, which means that, for example, x and x prime are indiscernible as a tangenter exactly when for any left type, or any type that way, if one belongs to T, x prime belongs also to T. So they belong exactly to the same types. And we see that types is a way to classify, but which is more rich than partition, and given things can be classified in multiple ways. So if we go back to the Peano or Russell's abstraction principle, I can reformulate this that way, which usually I put this that way. Oh, no, it's okay. It's another way to interpret F. In the former case, F was interpreted by equivalence class. Now it's interpreted by the set of the left types of X. Okay, but it's a solution to this equation. It's a way, set theoretically, to interpret F, which is okay in any situation, exactly as the class operator was a standard universal solution for definition by abstraction. The set of types is a universal set theoretical solution for the generalized abstraction principle. That's the idea, okay? Now, actually, it's a hard solution because here it's a set of sets. A type is a set, and the set of this is a set of sets. So it's a hard. It's from the abstraction point of view for set theoretically, it's not so evident. For example, it means more things. Okay, so we generalize the Peano Russell proposal to interpret F by a class, and you see, you'll not really see, but it's very generic. So many other situations can be thought as particular case depending on the property of R's. We will give it. So now very quickly my more mathematical slide. Actually, to go fast here will not be very pedagogical, but the slides will be so maybe I will do directly. So that's the definition of the notion of type. So we have two sets, x and y. Now a relation from x to y as on the blackboard. A prime will denote subset of x, and B prime subset of y to fix things. So we define two operators, one from that direction, from subsets to subsets, and one from subset to subset. That's those operations. And they generalize the class operator, as we'll see later. And now we define, these are defined there. So if A is subset of X, subset, the orthogonal, the right orthogonal of A will define as a subset of Y, with which any element in Y is in relation with. So intuitively, you have a subset here, and you exactly determine the subset here where the things are indiscernible from that point of view. So it's a point of view for indiscernibility, subset. Okay. Now the indiscernibility is appreciated from a subset, not from one single element. So we have a subset from this subset A. Okay, and here the the notion is a dual, so the other way around. Okay. Sometimes we distinguish by putting this on the left or the right, to say, but sometimes we just put everything on the right because A and B are subset of one or the other. It's clear from the context. And also the second slide, maybe. So we can introduce this terminology. We can say that so to be a type means a subset here is a type if there exists a subset here of which is the orthogonal. So there is a subset, set of tests which say it's indiscernible from this subset point of view. If there exists a subset which considers that as indiscernible. So I introduce this vocabulary that the subset with respect to which there are indiscernible, I call it the generator of the type. And okay, so in general, there are some subsets which are not type, and a given type can be generated by different subsets. Okay, just to have an idea. And there is an alternative definition of what is a type. It's a theorem, if you want. It depends. B is a type, so B is a subset of Y, which is obtained from a given set of sets as it is able, if only if it is equal to this bi-orthogonal. Okay. So that's why generally in the literature we speak of the notion of type through the methodology of closure by bi-orthogonality. But I think this way to think towards the notion of type is more obscure than the first one. A type is a subset which is indiscernible from a given point of view. The point of view of some subset point of view. So it's more clear, intuitively. Okay, bon, I am almost finished. So, classifier le terme, with the notion that we have the classification too, but it's a multi-classification, it's no more partition. So it actually it's a lattice, but there are the anti-set, and by inclusion there are some structure, and here are the main property, but it's not closed by union. Types are not closed by union. But what is more important, they are closed by intersection, which means that there is a minimal type. Important because, as I explained, we have an operator which is a set of sets, which is very high, and because the set of sets, we can take the intersection still, so we can recover a level which is more, which is more okay. So no, empty set may be a type. The full set is already type. It's not closed by union, but it's closed by intersection. Hence, there is this notion of just in the case the relation is an equivalence relation. What is the structure of the types? There are empty sets and the partition. So actually, just here we see that it's a particular case also. Okay, well, I think yes, I said that already with my hand or with my mouth. Okay, so my conclusion. The construction of types as set closed by orthogonality appears to be relevant, I mean, correct, at least set theoretical counterpart to Hermann Weyl's ideal definition by creative, is a more general case of which I forget to say it, but I think it was written in my slides in Weyl correspond to the idea of ideal elements of Hilbert. So it's a set theoretical counterpart of it, even if Weyl then says, I don't care. If you want to have a counterpart necessarily, you can do it, but I don't care because in my practice, I don't use them. Okay, don't use them. In a sense, we can then, if we follow, we can follow Weyl, and we can consider type as ideal elements in a sense, but from this set theoretical point of view. And because the only place where I know the use of this notion of type in the case of proof theory and intersection with computing theory was this the Curry Award, isomorphism or more generally the proof-class program correspondence of formula as types. So types, in that case, are sets of programs which have common behavior, but through the correspondence, types are formulas which is difficult to understand because formulas for us is language, and we are speaking of a set of actions. So it could be a little bit disappointing. But I think, for example, typically, philosophically, we can go from this to language, because inferentialism exactly try to take for serious the idea that acts of language language produce effects, like program if you want, but they're actional in some sense, and that the words are some invariance of this kind of interactions that we have in language. Future direction, they are not possible to try to understand the structure of the type depending on the properties of a relation, to understand the condition to have cardinality, low level of cardinality around types, these kind of things, particularly from the purely mathematical point of view. That's my plan for the future.